Hello, my name is Preston Robinette. My partner in this project is Emily Mitchell. Andrew Ellis worked on this project in the spring of 2019, and our advisor is Dr. Eli Owens with the Presbyterian College Physics Department. And this is the training chessboard. Chess is a strategic two-player game. There are nearly 100 different rules to gameplay, and there are 6 different pieces with distinct moves. There's the pawn, the rook, the knight, the bishop, the king, and the queen. And each of these different pieces can move in a different way. There are 64 squares laid out in an 8x8 grid, and there are 32 pieces, 16 on each team. The hardest part about learning to play the game of chess is learning the different ways that each of the pieces can move. Not knowing the way that each of the different pieces can move often deters people from playing the game. To mediate this problem and to promote the game of chess, we wanted to create a board that showed the different ways that the pieces can move, even when people didn't know them themselves. So in this example, we have a rook on the board. When we pick up the rook from the board, the different ways that the rook can move are illuminated in green. In our board, we're going to use LEDs.
There are a few different parts to designing our board, and that includes physically building the board, to putting all the wires together, as well as doing the coding and the software elements, and we'll discuss all of these later in more detail. For this project, we will be using an Arduino Mega, which is a type of microcontroller. This is what we will use to communicate between the board and all of the code that we write.
So the first thing we needed to address was building the board, and to do this we decided to use a copper-clad board for a couple of reasons. The first reason being that we could ground one entire side of the board, and then we could make little islands in the board to separate our lights and to separate the nails that we're going to be using to detect if a piece is there or not. You can see the copper-clad board that Andrew's holding right here, and you can also see the little islands that we drilled. We needed to drill 64 different islands for the lights, and we also needed to drill 64 different islands for the nails that we're going to be using to detect the pieces there. So in all, we had to drill 128 different islands. The way that we drilled each of the different islands is shown in this video right here. In this video, Emily is using a drill press, and we've made a custom drill bit by hollowing out the middle. So we only have two pointy ends, which are going to make the circle for us. This is the time it takes to just do one, and then we also had to rotate the board for each island that we did to make it line up with where the drill was. After we built the board, we then needed to drill holes for each of the lights and each of the nails that we were going to put into the board. In this picture, you can see our finished copper-clad board where we've drilled all the islands, and although it's harder to see, we've also drilled the little tiny holes for each of our lights and for each of the nails that we're going to use. Next, we needed to figure out how to determine if a piece was actually on the board. And to do this, we hot glued washers onto the bottom of all the pieces. In this picture right here, you can see this is one of our king pieces, and we've glued a washer onto the bottom. The importance of this washer is to connect the 2 nails that we're going to be using. So I've said this a couple times before that we've drilled islands and we've drilled in holes for our nails to go into, but I've never explained what they're used for. The nails, as you can see right here, are going to be used to show if a piece is actually on the board. So when a washer sits on the 2 nails, it connects ground to the Arduino. So when the Arduino reads a voltage of 0, it knows that a piece is on the board. When the washer is not on the board, then the Arduino is going to read 5 volts, so it knows that a piece is not present on the board. In this video, we show how the detection sequence works. Although it's hard to see, the words that are going on top of the screen are saying click, 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 click. So this is in comparison to when a piece is on the board. So when Andrew is clicking this button, it's sending a 0 volt, it's sending a ground voltage into the Arduino, telling that a piece is there. So when he's clicking, it's showing that it's clicked. And this is similar to us putting a piece on the board and showing that a piece is there. Now that we know if a piece is on the board or not, we next need to identify what that piece is. And to do that, we use an initial matrix and a piece matrix. An initial matrix keeps up with whether a piece is on the board or not. And we initialize it with how we set up the board in the first place. So in this top left corner, our initial matrix is 0, 0, 0, 0, 0, 1, 1, 1. The zeros, like we said before, represent ground. So that means that a piece is on the board, because the washer that's on the board is connecting the ground plane to the Arduino. The ones represent that a piece is not on the board. So we're continually checking for a change in this initial matrix throughout the process. Our piece matrix keeps up with what piece is what, so each number represents a different piece. So 1 could be a rook, a 3 could be a queen, and for this example we'll say that 2s are pawns. So as we're continually checking our initial matrix, we notice a change. So now that this number is a 1, we know that this piece has been moved off the board, because zeros represent that a piece is on the board, and 1 represents that a piece is not on the board. And then we check our piece matrix to see what that piece was. So from the piece matrix we know that this is a pawn, because a 2 represents a pawn. The next thing we do is to see where the piece is moved to. So we're looking for another change. So in this example, the pawn is moved 1 space forward, because zeros representing that a piece is present has been moved from this location to this location, and a 1 is now in this location, saying that there's not a piece there. And then our piece matrix updates to represent this information. So a pawn has been moved 1 space forward, and now there's no piece right here. And this is our final initial matrix, showing that we have pieces right here, 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 and we don't have pieces in these locations. And this once again shows the different pieces that we have on each location. After we had made our board and we had figured out how we were going to detect if a piece was on the board and how we were going to identify what that piece was, we next needed to wire everything together. So this involved soldering in each of the LEDs into the squares and soldering in the nails that were going to detect if a piece was there or not, and then connecting each of these components to the multiplexers and then from the multiplexers into the Arduino. As you can see, this is a lot of wires. There are 64 inputs and there are 64 outputs on our board. So that means there are 128 different wires, and because we need a wire going to ground and we need a wire going to 5 volts for each of these components, that means we have 256 wires coming off of our board going into the multiplexers. The multiplexers, which we'll talk about later, also require a large number of wires as well. We need 3 for timing, 1 for the common in-out, which is going to run to Arduino. We need 1 for 5 volts, 1 for ground, and we have 16 different multiplexers. So this is a total of 96 wires that are going into our Arduino. You can see it's a hot mess. It's crazy. Ah! So the board that we left off with at the end of last spring is on the left, and one of our goals was to make a cleaner casing for our board, which is in the middle. It's a wooden board, and if we need to work on the bottom components, we can slide out the bottom of the board and flip it over to work on the bottom. At the top of the board you can see each of our different LEDs, and you can also see the nails that we're using to detect pieces. Here is an example of a washer sitting on top of the nails, which are all glued onto the bottom of our pieces, and this is used for detection. The right shows the comparison between our old wiring and our new wiring. So for these, we took wiring and cut them specifically for the lengths that we needed for our board, and then we used these blacking casings to run the wires to the PCB, which holds our multiplexers and which will also run to the Arduino. Unfortunately, we ran out of time and weren't able to solder everything together, but we were able to solder in a few components onto our PCB.
Here is the printed circuit board, or PCB for short, that Preston was just talking about. It definitely helped us condense our wires and put everything together in a much more orderly way. Up at the top part of the screen, you can see the actual finished design that we sent off for manufacturing at Osh Park. We created this design through a program called KeyCAD. Down below, you can see the physical board that we received in the mail that we're using to construct our final board.
We use multiplexers to minimize the number of wires that we have going into the Arduino. We don't have enough spaces with the given number of components that we have coming off of the board to run into the Arduino. Using the multiplexer, we can take 8 lights, or we can take 8 nails and plug them into one multiplexer, and then have one wire going from the multiplexer into the Arduino. This is the leg that we would use to go into the Arduino. It can either be an output or an input, so it can either be our lights or it can be our nails, and then we can plug in 8 different lights or 8 different nails into each of these different legs. These 3 pieces right here act as our timer, and these switch between which channel we're reading. The reason this is so beneficial, so instead of having the 8 rows act as one block, we can still have them read as individual individual squares. This is similar to if you have a light switch and the light's on, and you're flicking the light switch on and off so fast that the light stays on. So it looks like it's continually staying on even though you are turning it on and off at the same time. Multiplexer works in the same way. It's switching between the channels so fast that it looks like it's reading all the channels at the same time, even though it's not. In this picture right here, we have a multiplexer in the middle, and we have 8 different input signals going into the multiplexer. And even though we only have one wire going to the Arduino, we can still tell which button is clicked, which is important for detecting pieces on our chessboard.
On the left-hand side of your screen, you can see the code that we used to be able to implement our multiplexing. It's simply just code that helps us with timing and being able to have it run through all the different channels that we want it to. As far as the rest of the coding goes, there were quite a few different pieces that we needed to be able to implement in order for this to be successful. The first part was being able to track the different pieces and where they were on the board at all times. After we were able to do that, we needed to be able to detect if a piece was removed. If a piece was picked up off the board, we need to be able to figure out which piece that is, and this involves being able to read input in from the board consistently. After this, we need to figure out which lights need to turn on based on which piece was picked up. After that, we have to be able to figure out if a piece was placed and where that was placed, and then update its location on the board. And finally, turn off all the lights, reset everything so that it's ready to go when somebody picks up another piece. In order to successfully track where all the pieces are on the board at all times, it was imperative that we assign numerical values to each of the different pieces. You can see here that we not only differentiated between the different types of pieces, but we also differentiated between the pieces on each team. These numerical representations of different pieces are placed into something called a piece matrix, and piece matrix is what we're going to use to track the location of all the different pieces. Now, piece matrix is just a numerical representation of an actual chessboard, as you can see in the comparison here on the screen. In order to determine if a piece moved or not, we needed to create 2 different matrices. This first one is called change, and this change matrix is going to be continually updated with the board in real time. The other matrix, which we call check, is going to be the matrix that we compare the first matrix change to in order to see if there's been any kind of change in the matrix. In order to continually update the change matrix, we have to read input in from the board. This is done through the multiplexing. Here you can see how the change matrix is being compared with the check matrix. Now, interesting things only happen when the change matrix is different from the check matrix. This means that there's been a change detected in our board. Basically, that we've either picked up a piece or that we've placed a piece down. When this happens, we call something called the piece function. We'll talk more about the piece function in a little bit, but basically the piece function figures out what piece was picked up or placed down, what lights need to turn on, and it turns them on for us. Now, after we call the piece function and figure out all the stuff that went on there, then we update the check matrix to be the same as change. So we've basically updated the stored memory locations of where all of our pieces are. Once we've detected that a piece has moved, we need to figure out what piece it was that moved. This is where piece function comes into play. Within the function called piece function, it goes to the piece matrix, which we talked about earlier, to figure out what piece it was that moved. Recall that the piece function holds the number identification values for each of our different pieces. Now within each of these different pieces, the value is read into something called piece ID, and this piece ID goes into the switch statement seen here at the bottom of the screen, and this will figure out what different function to call for each of the different values. For example, if piece function found out that it was a rook that was moved, it would call the function rook moves. Within the rook moves function, it updates something called LED matrix. LED matrix is simply a matrix of either zeros or ones, where 0 says don't turn on the light and 1 says turn on the light. Then the last thing we do in our main body of code is call something called the light function. The light function reads in the LED matrix and turns on all the lights that are labeled with a 1 and turns off all the lights that are labeled with a 0. Even though our full-size board is still under construction, we were still able to create a 3x3 board to test our code and its functionality. These are the multiplexers, which allow us to control the lights and the touch points in a minimalistic way. Here, these grid lines can help us visualize what the board looks like.